Hey homies, I hope you all had a good lunch. So hopefully you'll be able to fend off your nap, your post-lunch nap for about 20 minutes. So give us 20 minutes, and then you can do what you want. Eduardo and I are here to talk a little bit about XR graphics in Unity. So who here cares about graphics? You can put your hands up. Oh, okay, because I actually planned for nobody to care about graphics. And then we could just wrap it up and then go home. But it looks like we have to do this presentation. Okay, so since we do care about graphics, graphics are, marginally important to the XR experience. So they're responsible for delivering the visuals that drive an immersive XR experience. So what Eduardo and I wanted to talk about are kind of what the XR graphics team does at Unity, what we've been working on to improve the rendering experience, and kind of give some background onto some of the history of these, what these features are. Our primary concern for the team is performance, right? Performance is the main limiter for delivering content in an XR scenario, right? The resolutions are high, frame times are low, and if you kind of miss any of those targets, you'll break immersion. We're going to be a little bit different than I think a lot of the other presenters here who talk a lot about innovations in content development. So instead, what we're trying to do is we're trying to, unleash developer creativity by making sure graphics aren't a barrier for them. So hopefully after this presentation, you'll be motivated to go talk to your team about trying out some of the newer features, and hopefully they'll help fulfill your XR vision. So who are we? So this is Eduardo Chaves. He's an XR graphics engineer. And I'm Rob Srinivasiah, a senior XR graphics engineer. So I'm just a little bit older, is what it is. And so this is the agenda, right? So it's two rendering secrets we are experts don't want you to know. Or we do want you to know. So we're going to cover render viewport scale and single pass stereo, followed up by some time for Q&A. All right, and so now Eduardo will take you through render viewport scale.
All right, thanks, Rob. But before talking about what render viewport scale is, let's see the problem that it's actually trying to solve. So on your average 1080p game, we render in the process around 2 million pixels per frame. If you go 4K, then we're talking about 8 million pixels per frame. Now VR, if you take into account the eye texture resolution, the lens scale, and also the fact that we're rendering 2 eyes, that puts us on around 5 million pixels per frame. That's a lot of pixels already, but we need to take something else into account, and that's frame rate. So 1080p games, you can get away with rendering at 30, and that means you're processing around 60 million pixels per second. On a 4K game, also at 30, means you're processing around 240 million pixels per second. Now VR, we all know you have to run at 90. So that means that we have to process a whopping 450 million pixels per second. That's almost twice as much as 4K. But impressive numbers, but who cares, right? It's not like it's hard to make your game run at a constant frame rate, constant 90, and never dips. Well, as developers, we know that we spend a lot of time optimizing our game. But sometimes there are those pesky scenarios that insist to drag our frame rate down. And for those specific cases, it would be just good if we could render less pixels. So how can we achieve that? I think the first naive solution would be, why don't we scale down the eye texture? Just render on a smaller texture. And plus, Unity has the render scale feature that it's already built in. We could maybe use that. Well, there are a couple of problems with it. The main issue is that's going to cause a lot of texture reallocation if you do that dynamically. And in DirectX 11 and OpenGL, this is really, really bad for perf. And also, render scale is actually meant for matching the lens resolution after we do the warping, and also if you want to do super sampling. So that's not a very ideal use of our render scale. OK, so attempt 2. What if instead of scaling the texture, we just render to a smaller portion of the screen? And I like to point out that the scale of 0.5 actually means you're multiplying by 0.5 the width and the height of your viewport. So at the end, you're actually rendering 1/4 of the pixels, not half. And that's going to be important later, so please keep in mind. And so rendering to a portion of the screen, that sounds an awful lot like viewport. So why don't we scale the viewport? There's no texture reallocation, and at the end, we can just upscale it to the display resolution. That's a good idea, and that's what we end up doing. So how can you use this right now in your game? Well, first, you need to know how long your last frame took to render in the GPU. And you can do that by using our try get GPU time last frame function. And then once you have that time, you pass it to your own custom function that's going to decide the best scale for that case. And then you simply set the render viewport scale, calling vrsettings.render viewport scale. But please know that the get GPU time function it doesn't work currently on mobile. Okay, so that custom function that decides magically what scale you want to use, how do you implement that? What does that look like? Well, you can do that many ways, but one of the ways you can do is, well, let's say for 90 FPS, you have 11 millisecond frame budget. If your last frame took 13 milliseconds to render, you divide 11 by 13, you get 0.84. But remember that we scale the width and the height. So this is not completely the scale that we want to use. This is actually the square of the scale that we want to use. So the square root of that gives us around 0.91. Could you use that number already just to set the viewport scale? You could, but what if next frame you compute 9.2 or 9.0? So that's going to lead to some pixel wiggling and doesn't look as good. So what we recommend is have a table of discrete values in scales and select one based on what you need. And okay, what other cases can we use render viewport scale? We just talked about adaptive scale. But let's say you know there's a really complex scene coming. Why let adaptive scale kick in, but taking like 2 seconds or 2 frames from your player's experience before you can actually reduce the scale? You could just preemptively reduce the render viewport scale and make your player have a smooth experience altogether. He's not even going to notice that 1 frame hiccup that you had. Or gameplay events. Again, you know there's a big explosion coming, and you know there are going to be a lot of particles filling your screen and causing massive amounts of overdraw. So maybe it's a good idea to, for the duration of the explosion, reduce the render viewport scale. All right, so what's the catch? It seems too good to be true. It's actually not much of a catch. As you might have considered, the only problem we have here is when you're sampling a full screen, a screen space texture. Let's say you're doing some kind of image effects, post-processing. Well, before, you would call the text 2D, and you sample the texture just by passing the UVs that you get. Now, what we ask you to do is you have to declare this float 4 that we call it a ST float. It stands for scale and translation. And that float needs to have the same name of your texture. So Unity uses a lot of main text, so in that case, it's main text ST. And then what you do, you just call transform text, and you pass the name of the texture they're sampling, and Unity is going to take care of filling up all the correct values for you. Right? So that's it for render viewport scale. I'm going to hand it to Rob. He's going to talk about single pass stereo.
Thanks, Eduardo. So, I mean, Eduardo's not going to say anything about it, but he worked really hard to make render viewport scale work, fixed a lot of in-engine things, so thanks, Eduardo. Okay, so single pass stereo. So this is a relatively newer path inside of Unity. It's been in there, but it's kind of showing up on more and more platforms. But I wanted to kind of talk about what the background info for single pass stereo is. So this is our traditional forward render loop, right? These are the render stages that we go through in order to present images on our display. So we're going to start out by culling the scene graph to the visible object set, followed by generating our shadows, and then we can start rendering to the main target, right? So we're going to draw our opaques, transparents, and do post effects in the middle there too. And then after all of that, we can present to our display. So this is the normal single display set of graphics. Right, and so the initial implementation for VR in Unity was multi-camera or two-camera, right? So this is where you had one camera per eye. On one hand, this works and is the most compatible with pre-existing assets. So each camera is its own self-contained object, so you don't have to worry about interaction between the two eyes that much. So a lot of shaders, a lot of the normal render passes, everything kind of worked. But it's also the most inefficient, right? So doing two completely separate render loops doesn't really take advantage of any shared state that's between the two eyes. And there's actually a lot of shared state. So I think like the initial versions of the plugins were only doing like one camera per eye. I think the plugins have been updating, and so they're a lot better now. Even though we still support it in Unity, we don't, I think, recommend the use of them, but they still have some value. And so this is what the render loops look like for a multi-camera setup, right? You can see that both eyes go through the entire loop and then composite their outputs at the end, right? So just a quick note that these images, even though they're kind of like side by side, they're not actually like rendering in parallel or anything, right? It's going to do all of the left eye, then all of the right eye. All right, so that takes us to multipass. Multipass is an iteration on multi-camera. So there's a realization that some of the work between the two eyes can be made view independent. So we only have to do that work once. The culling and shadow maps are the parts that we can do independent of the eyes, and then we share the output from those stages. So this is what multipass looks like in the kind of render loop setup. So we have our shared cull and shadow pass, and then the work generated from that gets fed into a cut down left and right eye render loop. And then those images are composited and then sent to the display. So this is kind of what happens in GIF form. So all of the rendering happens to the left eye, then all of the rendering happens to the right eye. And so this, as far as like what your display targets look like, or your render targets look like, this multi-camera, multi-pass look very similar. So why do we want single pass, right? What are the benefits of single pass? To put it simply, it's getting two renders for the price of one. And everyone knows XR developers love a good deal. So single pass gives us a lot of performance. We get a big boost in CPU performance by taking advantage of shared state. So you might have already realized that even though we're rendering to two eyes, most of the state is actually shared between the two eyes. The shadows are shared, the scene graph is shared, the render target information, as far as resolution, anti-aliasing level, color format, those are all the same between the render targets, right? What's actually different are view-dependent matrices, so like your view, projection matrix, and the actual physical render target. Those are actually separate, right? But there's a lot of the things between the two eyes are very similar. So this is what our single pass render loop looks like. So it's kind of now very similar to what we were doing with the traditional render loop. So outside of the view-dependent stuff, we're doing a cull and shadows again, and then those feed into a single pass render loop that's generating draws for both the left and right eyes at the same time. And then this is the GIF version of that. So you can see that objects are being interleaved between the two render targets. Enabling is pretty easy. You just go to your player settings and then flip the stereo rendering method from multipass to single pass. Single pass is not owned by default, even though it's what we recommend and prefer that you use. It's not owned by default because it doesn't work for free. There's still some accommodations that need to be made. And we didn't want to break existing projects by just flipping it on right away. So what do we need to do to make sure that we're going through the render loop only once? So most importantly, we need to make sure all our constants are bound for both eye. So under the hood in the engine, it's setting up all the view-dependent constants into a shared constant buffer. And then the draws, the shaders themselves will index into these constant buffers. And we also need to make sure the render targets are bound for both eyes. Right? Toggling render targets is a really bad idea for desktop GPU perf, and it's catastrophic for mobile. It just like like if you know how tile-based deferred render GPU works, it'll serialize all the work by constantly toggling render targets. You don't want to do that. You can't do that. So we have two solutions. We can either bind a double-wide render target and then change the viewport between the left and right eyes, or we could bind a render target array. The render target array is kind of the more natural and preferred solution, but it's not so simple to index into the render target array on all platforms. So kind of the base case is we try and support double-wide, and then if the platform allows for render target array indexing, then we'll use that. So on PC and PS4 currently, it's a double-wide texture. And then Android and HoloLens, Android Daydream and Gear VR use a texture array. So what accommodations need to be made in order to make sure that you're selecting to the right portion of the render target? So texture coordinates for image effects need to be modified for double-wide. We have a lot of helper functions in Unity CG that will help with this. And a lot of the issues that will come up are from issues in shaders. It's just not using the right helper functions, and that's not anyone's fault. It's just something that needs to be done. So now we're going to talk a little bit about the perf, like what the perf differences are for single pass on the CPU. So this is our Viking Village scene that we kind of use for a lot of demo stuff. And there's some specs there if anyone wants to look later when the slides are published. So single pass perf differences are on the left you have multipass, and that frame took 11.94 milliseconds to render. And then on the right is single pass, and it took 7.3 milliseconds. And so something that's interesting is like the cull costs are the same because the culling is the same between the two passes. But then you can see that the actual rendering of opaques and transparents are basically cut in half, right? Because it's only now going through one CPU render loop instead of two. So the perf increase here is 39%. And so to really stress, like 39% is a lot to get back, right, on one thread. You can do a lot of cool stuff if you have, one extra CPU, like basically half of your budget, right, to do all sorts of great things. Or maybe it'll take you under budget, right? And now you're going from maybe stuttering at 90 to an even 90. So similarly as what Eduardo mentioned before, so what's the catch, right? So shaders are going to be the catch. Anything that has to do with screen space is going to present some challenges. Like I mentioned before, we do have helpers and macros to assist with this. Unity object to clip pass will automatically handle selection of the correct view projection matrices. If you're doing full screen texture samples, those need to be adjusted for double wide. And if you use the helper functions, that'll automatically do that for you. So this is like a quick shader code sample. So before, people would use the Unity matrix MVP constant, and instead we're asking for people to use Unity object to clip pass. And I think the shader upgrader takes care of some of these things, but you should be on the lookout in your own project if you turn on the single pass and you see some artifacts. And artifacts will look like this. You'll be meaning to render one image to one eye, but instead you get like these layered 2 to 4 images getting multiplied. And you'll notice right away something's wrong. And that's just some screen space effects isn't getting translated correctly. And this is a link later on that can be referenced once this presentation is published, or you can search on Google. You want to search for single pass stereo rendering and in Unity. And there's actually a really great document showing on like what kind of accommodations need to be made on your project in order to take care of single pass stereo. So wrapping up, I wanted to reinforce our team's desire for you to try out these new features, if you're not already. We think that they're pretty good about giving you back perf or stabilizing your perf, and you can use that to build a better experience for your users. This is just a pretty small slice of what the team's been working on, not just the VR graphics team, but graphics across Unity as a whole. There's a lot more coming down the pipe, and I think Unity as a whole has a lot of really great new graphics features coming that are really going to improve everyone's experience. And I think it's a really exciting time for Unity graphics, and I hope our developers are excited too. All right, Q&A time. So if you have questions, you can go to the microphones in the two little hallways here. This is the most exciting part of the presentation, the questions. I want questions.
Hi there. This is kind of a specific question, but I had a like a stereo video texture working way back in the day where you sort of had like a regular 3D movie and you could render one image in one eye and one image in the other eye to sort of get that stereo effect. Every couple of versions, I'll check back to see if there's a good way of figuring out which eye is rendering in the shader. It used to be we would just use 2 cameras for it and set the render flags, but it's too expensive. Every time I've tried the shader constant to figure out which eye it is, it hasn't worked. I haven't tried the latest versions. Do you know any consistent way of figuring out what eye is rendering in the shader, and if that is still able to be done with the single pass stuff?
Yeah, so there should be a constant. There's a constant buffer called, or I guess depending on the rendering method, it may not be a constant. It could be generated from an instance value. But there should be unity underscore stereo eye index. That should work.
Okay.
Obviously, if it's not working, we need to know, and we need to fix it. We want to know what that scenario is where it's not working. But that's a pretty reliable, or at least in my experience, that's what I use if I need to know which eye my shader is referencing.
Okay.
So we either populate that in a constant buffer, or we generate it in the vertex shader and then pass it on to the pixel shader. So if it's
interesting,
it should be available. Unity underscore stereo eye index, and as part of that doc, that single pass stereo doc, it references using that also. But it's available in multipass. It's not just exclusive to single pass.
Cool. I'll give it a shot.
Cool. Oh. All right. No more questions. Party pirate drink time, I guess, is on. Thanks, everybody.